Okay, good evening, everyone. So last time we have already finished the basic related to our metal oxide semiconductor field effect transistor, including the typical device operation, how the current will be inverted and then how the current will be flow, and also we have been discuss related to the equation, the current equation, and what will be the typical characteristic for the IDVD. So, but that is a basic. So for sure, for the advanced MOSFET, actually we are suffering many issues. So today we will start also focus on some additional concept. And these concepts actually are some of the issues for the MOSFET that we are still facing now, and probably is getting worse at the current transistor technology. So today we will talk about the additional concept for the MOS field effect transistor. So the first of all is related to some non-ideal effects. The first one that we actually want to mention is about the substratial hole conductions. So actually, although last time we mentioned that the current will be conductive as long as once the gate voltage is larger than threshold voltage, then we start to have the current through in the channel. The current will be inverted in the channel. But however, actually, still have the chance that even below the threshold voltage, we might still see that there's a small current. So if you try to plot the IDVG, but now we consider log ID versus the VGS here. So we actually previously we considered that the current, for example, we have the increase of a current as the gate bias increase, and then at a certain moment we will define this point as the threshold voltage. But that's in the linear scale. But actually in log scale, you will find out that actually below this threshold voltage, we start to see the current is gradually increase. So this is the experimental result. That's more realistic for the case that we are using for our transistors, that even below the gate voltage is below the substratial hole, we start to see the current here. So the drain current which exists for when our gate bias is smaller than threshold voltage is known as the substratial hole current. And this is because from the previously CV curve, we already knew that if you still remember our CV, we have a capacitance versus the voltage, and we already shown that the original is accumulation and start to have a depletion. And then we have this strong inversion. But there's a point here. This is a region where we call the weak inversion. So actually, this substratial hole region that still have the current is also related to this weak inversion region. So the CV characteristic is actually already suggests that even you start to have the weak inversion, you might start have the current flow in the transistor. So the Fermi level is close to a conduction band, then the valence band. So this is a condition that our VG is still smaller than threshold voltage, but the Fermi level is already close to the conduction band, then the valence band. So the semiconductor surface develops the characteristic of a lightly doped So we start have a lightly doped N-type channel. Where is this region? So now you can see once we increase the bias, at a certain moment, our Fermi energy here start to getting close to the conduction band rather than our valence band. So that suggests we start to have the lightly doped N-type region here. Lightly N-type. And this lightly N-type region also in the end will have the drain current induced in the channel, and therefore even beyond the threshold voltage we start to see this substratial conduction. And this region where our surface potential phi s in between the phi fp and 2 phi p is known as a weak inversion. So that's the first non-ideal effect that we should pay attention. That means that if even you try to bias at a gate voltage below the threshold voltage, we might still see a small current is actually conducting in your transistor. So that's the first non-ideal effect. And furthermore, we can consider the band diagram. So this is another way to illustrate. The previous, we only consider the band diagram in the one particular region. But actually, we can also consider the band diagram in the whole transistor, where we will have the source gate drain as shown here. So at the first condition that we have a VG smaller than 0 here. So the VG smaller than 0, and that means we have the huge barrier between the source and the drain because of due to this PN junction. So we have the built-in potential barrier, and this actually will stop the electron flow from the source to drain. So the electron is very difficult to flow to the accumulation. So that's why from the band diagram we can also understand that why there's no current. But at the point that once we start to increase our gate bias, but our gate bias still below our threshold voltage. So as I already mentioned that once we apply the positive bias in the band diagram, that means we try to pulling down our band. So the positive bias will cause the reduce of the barrier, and therefore you can see the barrier here is reduced, and the barrier reduced suggests that we might start have the electron be able to flow from this source to the channel. And this is the reason why we start have this substratial current. And also, for sure, in the last is a condition that our gate bias is larger than threshold voltage. So now this barrier is highly reduced, so your electron can be easily flow in the channel and reach to the drain side. So we can also understand how the current and the electron flow from source to drain by using the band diagram, which considers the source, gate, and drain side together. And also there's one equation related to substratial conduction, which is shown in here. And then this is a current in between. So for example, if we define the threshold voltage is 3.29, and then we can start to see below we still have the current. And also the 1.04, which below we still have the current here. So that's sometimes we call it substratial current or substratial hole conduction. And then the next non-ideal effect is what we call the channel length modulation. So the channel length modulation is happening when the MOSFET is biased in the saturation region, and the depletion region at the drain terminal extend laterally into the channel, in the end reducing the effective channel length. So what does this mean? This means that, as you know, once we increase our drain bias, then our depletion region in this PN junction can extend due to the large reverse bias. So the VDS increase, and therefore the depletion width increase. And once the depletion width increase, therefore your effective channel length this will be increased. And this increase suggests that actually your effective channel length is reduced. So your original channel length is here, but now your effective channel length is become the L minus delta L here. So that's how this sentence described here. The depletion region and the drain terminal extend laterally into the channel, in then reducing the effective channel length, which is our original L prime is our original L minus delta L. So that's our effective channel length. So the effective channel length conclusion is that actually will leading to the increase of the current here. So that's starting from the original equation here. This is an equation without consider additional VDS, but this is equation with additional VDS. So as you know, the additional bias, reverse bias, will increase our depletion width. So therefore this become larger, this will become larger. And then the delta L can be also calculated as shown here. And also our new current is related to original channel length over effective channel length here. And therefore our ID prime can be expressed as shown here, where we define as a parameter here. The parameter here, lambda, is called the channel length modulation parameter. And also this will cause additional, if you try to derive the ID prime over VDS, and then you can calculate this additional what we call the output resistance, which is related to this channel length modulation parameter here. But the main information the key is not to remember this equation. The key is try to understand what actually this channel length modulation will influence our current characteristic. So if you try to look at the IDVD here, so we have IDVD curve, and then the original, we should have this very beautiful IDVD characteristics that have the linear and saturation region. And because of the channel length modulation, so the channel length modulation suggests that this will increase, and this increase, this overall will decrease. So the L over this decrease actually suggests that in the end our ID plane is increased as well. So that means this is a curve where we start to have the channel length modulation, and this is because of this additional is mainly due to our L plane reduce. The L plane reduce, effective channel length reduce, is because of a delta L increase, and this is an issue that we call the channel length modulation. So this is a channel length modulation here. So in the end, it's not that difficult. So actually, it's not a very complicated issue. It's just that as long as we increase the drain bias and our effective channel length reduce, and then in the end, our current is increased. And the next non-ideal effects that we call the mobility variations here. So when we try to derive the ideal IV relationship, we assume that the mobility was a constant. But in reality, this assumption might not be true and should be modified for two reasons here. The first one is the first effect need to be considered is that the variation in mobility with gate voltage. So this is because of that actually when we try to, this is a typical device schematic, and we all know that once we start to increase the gate bias here, then we start have the formation of the electron in the channel. And then because of at the meantime we apply the constant VDS, so therefore this electron is be able to flow. These electrons are able to flow from the left to right and become the drain current. But this is the ideal case, what we talked about before. But what we don't mention is that this electron is still also, these electrons are suffering the gate bias here. So that means these electrons are also would like to flow from the top toward the gate bias, because our gate bias is a positive, right? So you can see the idea is how the electron flow from source to drain is because of these electrons are attracted by positive drain. But in the meantime, we also apply the party gate. So these electrons actually will be also attractive and try to flow from the dielectric and toward the gate side. And this will cause some variation in mobility, especially due to this surface scattering issue. So now the electron, actually the electron here are suffering the two different electric field. One is here and one is here. And there is an issue related to surface scattering is because once if our surface is non-ideal, has a certain defect, and then this electron will be trapped by this defect. So these are the electron trapping by the defect. Or let's say the previous one, we say the interface state. So once this being trapped, fixed at one particular location, and this is a negative charge. So negative charge will try to push away another negative charge in the other direction. In the end, that will cause what we call the surface scattering. So surface scattering will cause our mobility decrease. Will cause a mobility decrease. So anyhow, the surface scattering is always one of the big challenges, no matter for what kind of a semiconductor technology, always suffering the surface scattering. So that's why our transistor mobility is not that high as we expect. It's always much lower, and then the most of the reason is because due to the surface scattering issues. And second reason is that the mobility variation is that the affected carrier mobility decrease as the carriers approach to the velocity saturation. So this is another issue. That's what we call velocity saturation limit. This is because in the beginning, we always expect our mobility. This is our mobility versus our applied electric field. So we always consider that our mobility is linearly depends on our electric field. However, once our electric field is high enough, then we will start to see they will have the more velocity saturation. And because of this velocity saturation, that will also cause mobility variation. So that's actually the more realistic non-ideal effect that actually happening in our transistor. So here is some more details related to the velocity saturation. The carrier velocity increase until the ideal current is attained. However, we have seen that the carrier velocity saturate when increase electric field. And velocity saturation will become more obvious in the case of the short channel device. And the short channel device means that actually this is a device that has a smaller channel length. So means that the channel length L is small. And because of the channel length reduced, and then if you consider apply the same voltage that you will get a higher electric field. So the higher electric field will actually push the device, will approach to the velocity saturation. Velocity saturation will occur when the horizontal electric field is approximately reached to 10 to 4 volt per centimeter. So if VDS is 5 volt in a device with a channel length of 1 micrometer, and then the average electric field is 5 times 10 to 4 volt per centimeter. So velocity saturation is very likely occur in the short channel device. So if now we make this one not only 1 micrometer, we make a device with a 0.5 micrometer, then actually this electric field will increase, getting more. So that's why the statement here shows that the velocity can be more easily happen in the case with a short channel device. And once reach to the condition of the velocity saturation, now we have to reconsider our current equation where our ID set saturation current is equal to V times Cox and VGS minus VT and times V saturation. So that means in the case once the device is operating under the velocity saturation region, then it's crucial to know that now the current is independent of channel length, and the current is highly dependent on velocity saturation. So that means if we can find a device where it has a higher velocity saturation, that means this device, these materials is very suitable being used under this condition, because if the material has a high V set, of course in the end this device can have a higher ID set. So here is the reason that if you look at the different materials comparison, so we have the gallium arsenide, germanium, silicon, and then this is the drift velocity versus the electric field. Under the low bias, it's mainly linear dependent. But once you reach to the saturation, then you will find out that, for example, the gallium arsenide will start to see the decrease of the velocity. But however, this one, which is germanium, or this one is silicon, and then can show a higher, a little bit higher. This one can show a higher saturation velocity compared to the other materials here. Just want to mention that this is not I don't put any scale and unit here just to illustrate. This is a pure schematic to illustrate that the different material might have a different saturation, but it doesn't mean that for example, this will be higher than this in terms of how many orders. It is not reflect the values difference, mainly reflect that the materials can have a different V saturation velocity. So that's very important to consider, that if you find out that your device are actually very crucial to be operate in the high electric field, then we need to find out the one material that good for the velocity saturation. One example that we need to operate in the high electric field, and we also want the device to be operate in the very high speed. It's a RF power amplifier, the radiant frequency power amplifier. The radiant frequency power amplifier is mainly used on the lots of the cell phone base station. It's mainly used for the communication. So when we consider the RF power amplifier, we always want to operate in the high electric field, but at the meantime this device has a high speed. So at that moment, the velocity saturation has become one of the important consideration if we want to make it for the RF power amplifier. And for sure right now, none of these materials are good for the power amplifier. The only one that people believe is actually is ongoing, but it's already happening now, and but also will continue to dominate is a gallium nitride hand, because the gallium nitride has a very good saturation velocity. So that's why the gallium nitride is always a very good candidate for the RF power amplifier application. It's already actually commercialized. You can find lots of RF GaN for the power amplifier product. So here is a one example to compare. If previously we consider the constant mobility and velocity saturation, so the constant mobility will over optimistic for our current, which is not true, because in our device we don't have the constant mobility. But if you look at for the velocity saturation, then you will start to figure out that the current in our device is much lower, because of it's already operate into the region that can cause the velocity saturation. On the other hand, there's another phenomenon that we call the ballistic transport. So the average drift velocity is a function of the mean time between collisions. Or the mean distance between the scattering event. So in the long channel device, the channel length is much longer than the mean distance between the collision. So the average carrier drift velocity existed. But as the MOSFET channel length is reduced, the mean distance between the collision might become comparable to channel length, so that the previous analysis might not be valid. So if the channel length is further reduced, so the channel length is below our ballistic, the mean time, the L, which is the mean distance between the scattering, then the large fraction of carrier could travel from the source to drain without experience the scattering event. So this is the case we call the ballistic transport. So for example, if we consider the mean distance between the scattering, so mean distance between scattering is that if you imagine that you try to have the carrier flow to the one region, it must be scattering by some non-ideal effect, for example, the defect, the trap, or whatever. So this will be the mean distance that this carrier will be scattered. So if we consider the mean distance between the scattering is small l here, which is equal to 1 micrometer. So this is mean distance between the collisions. But now if we try to fabricate the channel length 15 nanometer, which is smaller than mean distance, so that means this is a condition we might start to have the ballistic transport. So that's also another non-ideal effects need to be careful. So most of the non-ideal effects getting worse once we consider the scaling. So scaling means that we try to make our transistor become smaller and smaller because we want to have a high density of our chip. So then we have to consider what actually the scaling rule we should consider. In the early time, actually, the scientists has already proposed that what we call the constant field scaling. So the constant field means that the principle of constant field scaling is a device dimension and device voltage must be scaled such as electric field will maintain as a constant. Both consider the horizontal and the vertical need to be remain essentially constant. So that's a constant field scaling here. So that means if you consider the left hand side, this kind of the device where we have the channel length, let's say 1 micrometer, and we have our oxide thickness 10 nanometer here, and in the doping concentration of 10 to 17. And also right now, because we want to do the constant field scaling, and then we consider the original bias in our transistor is a 5 volt. So now we consider the constant field scattering as a factor of 0.1. So that means right now if we want to have the maximum voltage in our transistor is 0.5 volt. So the one of the purpose to the scaling is we want to reduce the operating voltage. So now we reduce from 5 to 0.5. Then actually we also need to do the scaling in our transistor. So in this case, our dielectric become 1 nanometer, and our channel length KL here is become 100 nanometer, and also our doping will follow the rule of NA over K. That's a doping, which is become the 10 to 18. So in the early time, because our devices are relatively large, so it's fine that we do this constant field scaling. But now in the left-hand side case, then you can figure out that if you from the left device want to scale to the right, then it's become impossible, right? Because now our device has a 1 nanometer dielectric, which is very, very thin. That will cause a lot of reliability and gate current issues. So that's why, after a certain while, the idea of the constant field scaling is abandoned. We don't use this anymore because this one causes a problem that we cannot continue to do the scaling. But it's still good to have a little bit history review that the early time that how people consider for the scaling, and then the first concept come to the world is about the constant field scaling. And actually the typical K is around 0.7 per generation of a given technology. So that means that when we try to follow the constant field scaling in the early time, we try to keep the K factor as 0.7, and then with the following device circuit parameter with considering, for example, dimension, concentration, voltage, and so on. So that's the scaling rule in the early time. But still, it's not possible in the end. So that's why if you still remember back to the first slide introduction, actually it's already mentioned that there's one graph from early time to now, how actually the transistor try to follow the Moore's law. And also in the beginning is a constant field scaling, and then after we have some other scaling rules. So once we start to scale our device, and our device getting smaller and smaller, then we start to face the issue that we call the short channel effects here. So the short channel effect is also related to the space charge region, the depletion region between these two junction. So imagine this is a long channel MOSFET, and then so our L is relative large. So because our L is relatively large, so then we start to have the bias. This is a condition under the flat band condition. So now we don't provide too much higher bias. So then actually there's already the formation of the depletion region from the source to the substrate and also the drain to the substrate. And the depletion region here is shown here. Because our channel length is much larger, so at this moment our WSP is much smaller than L, so we don't have any issues. And this is a condition at flat band, this is condition at the inversion. So once inversion, we apply the VG here, and we start have the inversion channel. And because of our, this is long channel device, so the depletion region here and depletion region here actually won't influence too many inversion charges in the channel. So at this moment, the inversion channel is mainly controlled by the gate. So this is mainly controlled by the gate. So that's in the case with the long channel transistor. But again, once we start to decrease the channel length, then we start to have the issue that the fraction of the charge in the channel region controlled by the gate decreases. So as shown in the right hand figure, so now you can see this is a short channel device. So now we can start to observe that this is a part mainly due to our source to the substrate depletion region, and this is a part mainly due to our drain to the substrate depletion region. But because of our channel length decrease, so amount of the inversion charge controlled by the gate is only this portion. So in the last slide, you can see 99% of the inversion charge is controlled by the gate. But now, probably only 50% of the inversion charge is controlled by the gate. And then the rest will be influenced by the source to substrate or drain to substrate PN junction here. So this is the reason cause the short channel effect. So in summary, once we reduce the channel length, the inversion in the channel cannot be fully controlled by the gate anymore. And that's we call as a short channel effect. Of course, we can start to do the detailed calculation, but in here I won't show the details. I think this detailed calculation, that can be understood by yourself if you try to think about this. It's the same calculation, very similar to what we have been already talking about. But the main message here, which is this one, they will have the threshold voltage difference between the short channel device and long channel device, because of in the short channel device, part of our channel is not controlled by the gate anymore. The part of the channel is due to the PN junction. So if you try to look at the example in this one, I think this is a very simple one, so you can try to look up by yourself. And then this is just an typical question, try to calculate the threshold voltage shift due to the channel effects here. So with considering this doping, this channel length, this junction width, and this oxide thickness, and then the delta VT due to the short channel effect, which is a minus 0.0726 volt here. So that's around minus 0.07 volt due to the short channel effect. And with this calculation, actually, as I always say, that the example for the calculation sometimes not the main information I want to deliver in this class. This is just mainly for the exam, for the exercise, for try to put some equation and get some numbers that can probably make everyone feel more comfortable to prepare the final exam. But in reality, more important is this graph. In this graph, we don't use any equation, but it's coming from the real experimental result. So as we can see, the channel length decreased from 6 to 1 micrometer, and then we can clearly see our threshold voltage decrease. And then the threshold voltage decrease suggests that this is a short channel effect. So this is the issue. Basically, we can see from every kind of the semiconductor device. So we have channel length decrease or VTH decrease, and sometimes we call this as a threshold voltage roll-off. In the literature, you will find that some people call this as well. And as I say, this is mainly due to the PN junction. No matter from source to substrate or drain to substrate. And because we only bias in the drain side, so we can also expect that this threshold voltage roll-off is highly dependent on VDS, right? So you can see larger VDS, the threshold voltage decrease largely. And the reason behind, I think is right now should be very clearly for V1. Once we apply large VDS, then you can see the depletion region here is getting larger. So the depletion region here is getting larger for sure. The channel, the inversion layer under the channel cannot be controlled anymore. So everything is very consistent with the proposed model here. So this is one effect that we call the short channel effect. On the other hand, also there's another effect that we call the narrow channel effect. So the narrow channel is actually considered that this is the cross section where this is a channel width and this is actually our channel length. So this is channel length. So this is actually the region we mentioned here. So this is L and this is W. But now we try to turn around for this device schematic. So now we have W here and channel length here. And we actually find out that there's an addition space charge region at each end of the channel width, which is here. So this is an additional space charge width. Additional space charge width here. So this additional space charge is controlled by the gate voltage, but it's not including when we try to calculate in the threshold voltage relation. So in here again, it's not a key point for the derive. So I will just go straight to the conclusion where we can see the threshold voltage here is also influenced by the different W here. That's what we call the narrow channel effect. So this is another non-ideal effect that related to threshold voltage that you should know. So in the end, with considering the narrow channel effect, we can see that the shorter channel length we actually get the higher threshold voltage. So here is a conclusion between the short channel effect and the narrow channel effect. And to be honest, the short channel effect, sometimes we also call this as a SCE. And to be honest, if you try to make comparison between the short channel and the narrow channel, and more important is the short channel effect. This is one of the key issues that people are very actively discuss nowadays in every semiconductor transistor, no matter what kind of a transistor that you are working on, always suffering this short channel effect. So the SCE, the conclusion for SCE is that the first we'll see the threshold voltage decrease, and also, and because of the one thing that we don't mention, but just also want to let you know that because of this is highly influenced by the drain bias here, VDS, and also this is close to the source side if our channel is decreased. So there's a chance that this depletion region can extend to the source side. Even the channel is off, even we don't have a channel. And therefore, the electron can go through the depletion region and reach to the other side. So this is an issue that every scaling device all suffering. So that's why another phenomenon here is related to the leakage current. Is increased. So then this back to the first slide. When we talk about the evolution of our transistor from early time to the high K metal gate, I already mentioned that one of the issues is about the on-off ratio. And then we always want to make sure our off current as lower as possible. But once the channel length decrease, actually the off current is increased. And to solve this issue, that's why we come up with the SOI technology. We come up with the FinFET technology. So if you forget it, just back to the first slide to look at why at a certain moment people start to think about the SOI, why people start to think about FinFET. Because the reason is that we want to have reduced the leakage current, where is the I-off that we mentioned in the first slide. And then also, by using the SOI, by using the FinFET, we can get a better control of the channel under the gate, and then to avoid the leakage current. So that's the purpose we start to have SOI and FinFET. And another issues that we don't talk too much before is about the breakdown voltage here. And actually, the breakdown voltage, when we talk about the diode, we actually already mentioned, but that's mainly for the PN junction. Actually, in the dielectric, when we try to derive, when we consider the every IV characteristic that I was talking about, we always consider that there's no gate leakage current. So back to the transistor MOSFET schematic. We have a source, we have a drain, we have the dielectric, we have the metal. So now I think everyone in here can understand that once we apply the gate bias, for sure we have the electron, but at the meantime this electron will try to inject to the gate side, and that will become our gate leakage current. This is something that we ignore when we consider the current voltage equation, but in reality, this is something that we cannot ignore. And this can be understood by many different mechanisms. One is already mentioned that the reason why we need to learn the quantum mechanics is because we also want to understand why there will be the gate leakage current, even there's a dielectric, which is the insulator. Or by using the Venn diagram, it's the same. If you consider the metal gate oxide semiconductor, so we have the Venn diagram. This is our oxide, this is our silicon. And now we apply the positive gate bias here. So that means we actually start to pulling down the Venn diagram, not only for the SiO2 but also for silicon. And we already knew this is a region where we will have the inversion charge, but because of positive bias here, then the charge can start to flow from the right to the left and become the gate leakage current. And one of the reasons that the electron can start to from here jump to here, in the quantum mechanics we call this as a tunneling effect. And the tunneling effect is highly related to the barrier here, but also related to the thickness. But now, due to the positive bias, you can see the thickness here, original is a square, now become the triangular. So if you are the carriers sitting here, that means the barrier you see is reduced. The barrier you see reduced because original is a square, now become a triangular. So that means the walls, the barriers become thinner. So the barrier becomes thinner, for sure the tunneling probability is increased. So that's the reason why we will have the leakage current, gate leakage current. And this is usually what we call the FN tunneling. So in here, we won't talk about the FN tunneling, but once you start to conducting your research, in the semiconductor field, you will definitely face the FN tunneling issue. It's actually related to the electric field in the dielectric. But in anyhow, this just want to illustrate that actually we will face the gate leakage current issues. So that's why you will start to see this is a gate current versus a gate bias. This is a real measurement data that you increase the gate bias, you start to see the current increase. But at one moment, the current will continue to increase. At a certain moment, face the issue of the catastrophe value. So the catastrophe value means that actually we will have the huge current increase. The huge current increase suggests that the dielectric actually lose the insulating property. Right? So now we have a huge current here. It means that the original, this is insulator, we should have a low current, but now we have a very high current. So that means our insulator is not insulating, our dielectric is not the insulator anymore. And once this is not insulator anymore, then we consider this is the issue, what we call the breakdown. So this is an issue that we call the R-side breakdown. But the R-side breakdown is not only related to the gate voltage, also related to the time. So that's why sometimes we have another phenomenon that we call the time-dependent dielectric breakdown, TDDB here. So the TDDB is an issue that we have a gate current and we bias at one condition, for example 10 volt. So 10 volt is here. Ideally, the 10 volt should give a very small current, but as long as the time, your bias is longer enough, in the end you will start to see the current shooting here, and that's also related to the time. So that's why we call this time-dependent dielectric breakdown. And then TDDB is also one of the main reliability challenges in every semiconductor device, no matter what kind of device you are working on, memory, advanced transistor, CMOS, NMOS, PMOS, 2D, whatever, wideband gap, we always have the TDDB characteristic. And here we won't talk too much why that we will have these TDDB issues, but in my another class is talking about the reliability. We will have the dedicated chapters to discuss about the reason that will cause this time-dependent dielectric breakdown. So this is also another non-ideal issue. And another one is what we call the average breakdown. But I think the average breakdown is something that not very new to you, because in our PN junction, we already mentioned in the PN diode, we have this IV characteristic. We already shown that the current will increase under the forward bias, but under reverse bias, in the beginning it's a flat, but after a certain moment we will see the large current observed here. So the large current observed here, that's because due to the average breakdown. But why we have to as I already said, that the reason to learn the PN junction is not only for PN diode, because in our transistor we have many PN diode. So you can expect this is a one transistor in the region between the drain to the substrate, and also this is another reverse PN diode here. So that means this junction can also suffer the avalanche breakdown. So, but the only difference here is that we bias the VDS. So if VDS is larger enough, actually we start also face the issue of avalanche breakdown. And therefore, this is because of this is a reverse PN junction. So that means, with considering the reverse PN junction in the drain side, if you try to plot the IDVD, in the beginning, we should have a very low current. This is a case of VG equal to 0 volt. But after the certain moment, due to this reverse PN junction will cause the average breakdown, then we start to see the current increase. And this is also due to the average breakdown. So the same phenomenon we talked about in the PN diode, now it's the same we can apply to the MOSFET, and then the physics are exactly the same. Phenomenon is exactly the same, just the bias condition is different because now we bias in the drain side. So another issues related to the breakdown is that we also call as a punch-through effect. So punch-through effect is particularly important in the case of the short channel device. So the punch-through is a condition at which the drain to substrate space charge region extends completely across the channel region to the source to substrate space charge region. So this actually is the one that we mentioned before, but now we will mention again. If imagine you have a one small channel, short channel device where you have the source here, you have a drain here, and this is a source, this is a drain, and this is the gate. As we say, once we increase our VD, so in the case without increase the drain bias, we already have the depletion rates in the drain side and source side, which I show me here. This is our depletion width, and this is our depletion width. But now, because our drain bias increase, so the depletion width in the drain side can further extend. So this one will be extend, and this one will be extend. So now we have a larger depletion width. But the issue is now you can see there will be a certain depletion width start to reach to the source side space charge region. So this is the sentence means here. And the drain to substrate space charge extend. This is a sentence means here. And because of right now your depletion width here is extend to the source side. In this situation, the barrier between the source drain is completely eliminated and the very large drain current will exist. So in this situation, the electron can start to flow from source to the drain and become the drain current. This is the electron flow direction, but the drain current is the opposite direction. So that will cause a huge current, and this is a situation we call the punch through. Why we call it punch through? Because the depletion region is punch through to the source side. So that's why we call it punch through. And this is the issues very serious in the case with a short channel device. So normally this will cause the characteristic like in showing here. First of all, at the Vg equal to 0, very high leach current. And also, there's no saturation region. So the similar things can be also understood from the Venn diagram. So the Venn diagram here, this is a source, channel, drain, and because our source is N plus, so this is N plus P N plus. And then, because right now, the channel, the barrier here is between the channel and source is high, so therefore, the electron here is not be able to go through to overcome the barrier. But once we have a large drain bias here, then we have an electron here. So now the barrier is reduced, so then the electric carrier can start to tunnel and across this barrier height, and then this will cause a huge drain current. So no matter which way, in the end, the phenomenon can always be explained. And another issue is what we call the lightly doped drain. So the lightly doped drain is that because of we know the junction breakdown voltage is a function of the maximum electric field, and as the channel length becomes smaller, the bias voltage may not be scaled down accordingly, so the junction electric field has become larger, and as the electric field increase, the near average breakdown and near punch-through effect become more serious here. So therefore, this is an issue that we need to try to solve. And to solve this issue, we will consider as a transistor design that we call the LDD, the lightly doped drain. So here is a schematic for the lightly doped drain. So this is original transistor, but now we try to put this a smaller N- in this region. This is what we call the LDD, lightly doped drain. So lightly doped drain can effectively to reduce the electric field. So this is the result of the peak electric field in the LDD. So the conclusion is that the LDD can reduce the peak E field in the drain side. Reduce the peak E field in the drain side. So that's the LDD. And also, related to the threshold voltage, there's one possibility that we can adjust our threshold voltage by using a process, what we call the ion implantations here. So the several factors such as fixed oxide charge in metal semiconductor wall function different, oxide thickness semiconductor dopant can influence the threshold voltage. But also the process related what we use for the ion implantation can be used to change and adjust the substrate doping near the oxide semiconductor surface and to provide the desired threshold voltage here. So the idea is that we will use the ion implantation to implant the acceptor outons. Here are implant into P-type substrate. So we can have this D1 to tune our threshold voltage to reach our target by using the additional ion implantation process. So the last one is also another reliability issue, and that actually is getting worse and worse now. Is because of we try to reduce the channel length, and in the end, the electric field is always become larger. Once the electric field becomes larger, then everything is getting worse. So as electric field in the drain space charge region increase, the electron hole pairs can be generated by implantation, and the generated electron used to be swept to the drain, and then the separate hole sweep into a substrate in the N MOSFET here. So this is a situation. First one, we actually have a VGS. So we try to have a gate bias. This is a situation that we provide gate bias, but also with a VDS here. And then we will find out that at this moment that some of the electron generated in space charge region are attracted to the oxide. Due to these are attracted to oxide due to electric field induced by the positive charge. So we will have some of this one will flow to the oxide, and this generated electron has an energy far greater than thermal equilibrium value, and that's why we call the hard electrons. The reason we call hard electron is because these are the energetic electrons. These are the electron has a higher energy, so that's why we call the hard electron. And these energetic electron, they will cross the silicon dioxide interface and then generate additional interface state. So then this will try to inject it, and in the end have the additional interface state happening here. And the probable cause of interstate generation is due to the breakup of the silicon hydrogen bonds. A dangling silicon bond is produced, which acts as an interface state. So that's one of the reasons. But the most important is the charge trapping in the interface state causes a shift in threshold voltage, additional surface scattering, and reduced mobility. So as shown here, we have the high electron will try to inject to the drain oxide, and at the moment it will cause this interface state. And this additional interface state will have the trapping issues. will cause the trapping issues. And this trapping issue will cause threshold voltage shift, surface scattering, and reduce mobility because we have a lot of electron trapping close to the drain side. So that's what we call the hard electron effects. And the most difficult part is that the high electron effects are getting more serious because as the channel reduce, and then actually the electric field is increased. The electric field increase, and then it's more easy to trigger the high electron effects. Okay, so we will take a break for 10 minutes, and then we'll come back for the BJT.礼拜一，是。
我跟你说那个，
对，
就这个为什么 LDD 可以有效的降低 E field？
主要是因为它的那个 depletion region， 因为你的 lightly doped 嘛，所以 depletion 会比较宽。宽的话，那你可以承受电压就，因为它的那个承受电压就是你的宽度乘上电。对的，那你拉宽的话，那你的 peak 就会下降。对。
可是问题是，这个不就是，这如果它变宽的话，不就会变成前面所提到 pump through， 就是那个
对啊，所以它
我的 overlap 会重叠的
我看一下你的这个情况的话，它一定还是会有，最终还是会有 punch through 的效果，所以这个是跟你的这个channel length 是它主要是降低我们的这个电场。它主要是可以降低我们表面的LDD。
你说这个是建立在说，我今天 pump through 就已经会产生了。
对。然
后我再制作这个 LDD 去
降低我们的这个表面电场。对，所以这个情况下，它当然还是要去考虑 short channel effect。
对。
还是会去考虑 short channel effect。对。对。
好，因为我那一直在想就是，那它的 diffusion width 不是更宽，然后就更容易 pump through。对，这个我不知道我这逻辑想对不对，就是。但因为前面pump through感觉就是，
你这个浓度变，看一下，你这边浓度变淡，浓度变淡的话，所以你对你的 depletion region 这边会
变宽，
对，所以它会更容易pump through。
对，可是它
可以降低表面电场。对，你的浓度越浓的话，它在这边的 depletion region 就会，depletion 跟我们的浓度成反比。对，浓度越浓，你的 depletion region 会。
浓度越浓 ，depletion region 会下降。
对，越窄。对，所以你浓度越淡的话，
所以我原本是想说，如果要避免 pump through 的话，这边不是应该要？
我觉得它这个不是为了要，避免 pump through， 它只是为了避免你的这个电场让它产生 breakdown。对，但是它同样的也是一样会产生 pump through 的效果，它没有办法保证 LDD 可以解决 pump through， 但可以保证你的 LDD 可以避免在 drain side 会有这个 impedalization。对，主要是这个意思。对。然后因为你 surface 表面电场也降低，所以你也可以减少 high electron effect。对。
好。那老师，这个 velocity， 这个 saturation， 这个 velocity saturation 是因为
它跟材料的有关系。对，它这是有点复杂，你要看一下教科书。基本上它是很多的结果的成因造成的。对。
然后还有一个就是，因为上次功课好像先出到这边。
对。
然后我就先去看一下，可是我对这个东西，对这个公式我不是很。
这就是 diffusion width 啊。
对，可是 diffusion width 不是应该是我今天如果是 P 刚刚。
对。
然后我给的电，假设给的 VG 好。
对。
所以我这个地方，就是我不是应该是2 psi SP PG
对
乘 QNA， 然后
对
开根号。
对。
可这个 Psi FP 感觉上好像是就是一个那个 band diagram 里面这个 EI 到 EF 的距离。
对。
这样感觉好像不是施加。
这个才是施加的，施加是在这边。
在这边。
对啊，这是有施加。这个应该是 flat band 情况下，就是本身在没有偏压情况下。对，这个是不是 flat， 这是没有偏压情况下。没有偏压情况下，你就两偏这样子，它本身没有偏压情况下，它本身就有 diffusion rate。
OK。
对的，好，这个是有加偏压的。
好。
对。
好。
对。
好，谢谢老师。
Okay, so let's move on to the next transistor. This transistor actually, it is also very important, but in most of the semiconductor class, we always put, some professor will put this before the MOSFET. So they will first to talk about PN junction and talk about bipolar and then talk about MOSFET. And that will cause the issue that normally we don't have enough time to MOSFET. And then my feeling is that always I want to put the MOSFET for the higher priority because of the MOSFET is the most crucial device, also related to the feedback and some of the vent transistor. But I don't mean that actually BJT is not that important. Actually, bipolar junction transistor is also very important technique. In the past, this can be used for the logic, but nowadays the BJT is mainly used for the some of specialty. Of course, the application for BJT is a little bit decreased. It's not widely used, but as I say that in the MOSFET we have many parasitic PNP junction, and this always causes some non-ideal effect that actually has the same physics that is coming from the BJT. So that's why the bipolar junction transistor still will be the very important technology, but also need to be well understood, and then but it will take. It's actually much more complicated than MOSFET because we need to consider two PN junction, and then we need to consider electron holes interact with each other. And recently, I just realized that one of my students just got the job offer coming from the TSMC for the 2 nanometer device engineer. So when we talk about 2 nanometer, we always think about probably it's advanced FinFET gate all around. But one of the surprising things that the manager who interviewed him actually asking him a lot of questions related to the BJT. So he asked about how's the BJT operation, what's the physics inside, even asking about the issue of electron. So still, that means that probably, of course, I will not able to very precisely understand why he will ask this issue, but it must be somehow in the advanced transistor below 5, 3, 2 or future, we still need to pay attention to the issue coming from the BJT. So in this chapter, we will talk about the bipolar junction transistor, which in short, we call this as a BJT. So the structure for BJT is not that complicated. Actually, if you look at the structure here, it looks like a little simple compared to the MOSFET. So in the BJT, actually the structure can be drawn as shown here, which is a structure that we have for example, in the left hand side, we consider this as a NPN BJT, but actually it's not exactly the NPN, but actually it's a doping concentration with N++, P+, and N here. And then we call in the middle, we call this as a base region. And in the left hand side, where we have the high concentrations, we call the emitter. And then in the right hand side, that we call this as a collector. So if you try to put the circuit symbol, that would be like in this way. So we have the base here, we have the collector here, we have the emitter here. And also, because this is considering for the two PN junction being connected with each other, so we have the two PN junction, which one is this one. That's we call the BE junction. And then another one, that's we call the BC junction here. So we have two. One is a BE junction, another one is the BC junction. So this is a typical case for the NPN BJT. But we also can have the structure in the right hand side, which is PNP BJT. PNP BJT. And then similarly, we have a P++, N+, and P here, and which this one is our base region, and which this one is our emitter region, and this one is the collector. And then the circuit symbol for the BJT is show me here. So if you have followed the electronics under the undergraduate class, or yeah, usually you should, for most of the engineering or EE engineering background, probably you will follow the electronics 电子学. So in the electronics, in my generation, the first circuit we have to understand is a BJT. So, but that will give us some, and then the later will be the MOSFET. So we will first talk about physics, and then we talk about the BJT based circuit, and we talk about the MOSFET later. But that gives us some of the wrong impression that the MOSFET is difficult, because we are in the past, in my generation, I was being lectured that the MOSFET being put in the last. I'm not sure for everyone, but if you are in the double E background, we have electronics 1, 2, 3, and then usually MOSFET is electronics 2, and then the third will be the very advanced. So that actually causes some impression that the MOSFET is getting complicated than the BJT. That's why the professor will lecture the BJT in the beginning and move on to the MOSFET. But once you understand the physics, semiconductor physics, then you will figure out that actually MOSFET is way simple than the BJT. But I'm not sure why that in terms of the circuit level lectures always, at least in my generation, they always put the BJT in the beginning. If you also not sure for your lecture or not. But in anyhow, I would say the BJT is a little bit more complicated, that where we will explain later. So then the basic doping for the BJT here, as I shown, is NPN. Then where we have this is a concentration of ND minus NA. So from the left to the right, which is N++, P+, and then the N. So this is the basic doping schematic. In terms of one BJT, we will not dope everything in the same concentration. We will have the concentration difference. That has a purpose. We will talk about this later. So in terms of the operation mode, actually we can divide the BJT by considering the 4 different operation modes, which this one, first of all, because we have the two the PN junction here, so then we have to consider the bias between the collector and base, that's we call the VCB, and also the bias between the base and emitter, that's we call the VBE. And in this case, that we can divide by 4 different operation regions. The first one is BE forward bias and BC reverse bias here. So this is let me put some. This is BCE here. So the first one we need to consider is a BE forward bias. For BE forward bias is here. This forward bias and this reverse bias. So this is actually when we try to bias in this region, forward active, because right now the BE is positive, so that means this junction is forward bias. But now this is a VCB, so this VCB is a positive, that means this PN junction is reverse bias. So that's in the case we call this as forward active. So by consider this case, we have 4 different scenarios. For example, we can also have the case that the BE forward bias and BC forward bias, where will be this region. That's what we call the saturation. And also we can have this region where BE reverse bias and BE reverse bias and BC reverse bias. And this is we call the cutoff region. And the last one is just a completely reverse compared to forward activities. That's what we call the inverse active region. So basically, when we try to operate the BJT, is considering that each junction is being under reverse bias or forward bias or not. And then one of the difference between MOSFET and then the BJT is that actually the BJT is a current drive transistor. So we need to have the base current. Show me here. So we have to also consider the collector current. So we will use the base current IB to turn on our transistor. And that's we consider this as a current drive transistor. So that means the output IV characteristic here, what we are interested in is a collector current versus VCE. And then actually some are very similar to MOSFET, because in the MOSFET what we care is IDVD. And if you look at this, you consider this as a MOSFET. Where is the D? This is D. Where is the ID? This is ID. So now we consider for the BJT, this is IC, and we consider the VC here. So the output characteristic actually is very similar to the MOSFET, which also have the linear saturation, and linear saturation. And also, as I say, this is a current drive transistor, so actually we will increase the base current here, then we'll have the higher collector current. So that's the basic idea for the IV characteristic for the BJT. And then in reality, actually, although in previously we mentioned that this is our schematic for our device, but in reality, we are not possible to make a device like in this way. So in reality, what we can really fabricate is a transistor like here. We have the N collector as a substrate, and we will implant one region as a base, and we will implant a smaller this as a loss of an emitter. So each one, NPN, each one is a 1 BJT, right? And this one is a NPN, and this one is NPN. So that's a real device schematic, and then we will connect everything, emitter together and everything base together to the one terminal. So that's a real fabricated device schematic for the BJT transistor. But now we have to come back again to start to analyze the carrier distribution. If you still, we just finished the MOSFET. In the case of MOSFET, we never talk about the carrier distribution. But the last time, when did we talk about carrier distribution? It's under the case of the PN junction. So this is because of the current transport. If you still remember the conclusion for the PN junction, how do we determine the current characteristic. There's a one sentence, one conclusion say that the current transport in PN junction is dominated by the minority carrier. So when we analyze the PN junction, we already try to use a minority carrier to understand the whole current characteristic in the PN junction. Now we will play the same way again to do this analysis on the PN junction. So the most important part for the BJT is to understand the minority carrier distribution in the PN junction. And then we have to understand the minority carrier distribution in the different modes. The first one, the most important, is the forward active, where the forward active is a BE junction is under the forward bias, but the BC junction is under the reverse bias. So now let's just try to draw the minority carrier distribution once. You have to draw it by yourself once, then you will understand, because if you just look at the textbook, sometimes you will be overwhelmed, you will be scared, you will be shocked by how complicated this distribution can be. But if you do step by step, actually it's not that complicated. So this is a minority carrier distribution. Then first we will divide by 3 regions, where we have an emitter, on the left, and we have the base. In the middle we have the collector, right? And then because of so we already mentioned that the doping concentration is not the same. So although this is NP, but actually it's N plus plus, P plus, and N. And then because of what we are trying to draw is a minority carrier concentration. So because of this is N plus, so we can expect that this doping concentration in the emitter, the majority carrier is electron, is a P, and therefore the minority carrier must be the P, where is a hole, which is a P PE0. So the 0 means that this is under the equilibrium condition. So this is a minority carrier concentration in the emitter. And also similarly, we can start to have the minority carrier concentration in the base region. Roughly will be here. N will be here, where this one is NB0 and this one is a PC0. Okay, so that's the first step. We plot all the minority carrier static, the equilibrium minority carrier P0, NB0, and PC0. And then in between, because this is a BE junction and then this is a BC junction, so we also have to take into account the depletion region. So we will have the space charge region in between So this is our space charge region in between the base emitter and then the base collector here. And now we can also define the several different coordinate here. The coordinate between the emitter is defined this as x prime equal to 0, and this is x prime equal to xe. So this is a coordination of x prime in these directions, and also we can define this x equal to 0, and this will be x equal to xb. So this is a x coordination in this direction, and we can also have the x prime prime equal to 0, and then x prime prime equal to xc. So that's a x double prime coordination in this direction. And the reason why we have to consider coordination here, because now we will plot each region, the minority carrier distribution. Then the first thing is that this is the case here, because right now the BE junction is under the forward bias. So in the case of forward bias, actually the holes will flow to the left, and then the electron will flow to the right. So that's a forward bias if you go back to check the PN junction. So therefore, we can plot the same minority carrier distribution in the similar of our PN junction under the forward bias, where we will have here, which is a PEX prime prime. That's our PE, which is a minority carrier distribution at the X prime position. Sorry, this is X prime position. And from previous lecture, we already mentioned that actually this minority carrier distribution will follow the exponential decay. So with a certain distance, this will reach back to the PE0, right? So this is exactly the same graph we draw for the PN junction. If you forget it, you can go back to check. But similarly, we can also start to draw this one. This is a NBX. This is NBX. And because of, ideally, if we consider the only one PN junction, this should be like this way. If you go back to check the PN junction, when we try to plot the minority carrier under the forward bias, we have this distribution here, we have this distribution here. So that's once we consider the only one PN junction. But now we have another PN junction here, and this is under reverse bias. The reverse bias means that at this moment, the carrier, the minor carrier will become 0, right? The reverse bias is that we given reverse, we completely depleted, and then there should be no carrier. So this position should be 0. So that will force the minor carrier concentration here will follow decrease and force to be 0 at the edge of x equal to xb. So that's the only difference between the PN and then the BJT. Then let me say again, in the previous case, when we talk about PN junction, this will come back to the NB0. But now, because we have additional B is under the reverse bias, and this will force the minor carrier concentration here to be equal to 0, and therefore our concentration distribution profile will be shown as drawn in here. And similarly, this is under reverse bias. So everything should be always starting from 0. But in the end, it still will come back to reach to the PC0. So we will have the profile like here. So this is PC XS prime here. So that's the first minority carrier distribution in the case of a forward active, where B is a forward bias and BC is a reverse bias. And the same, we can start to try to draw in the case of the saturation, where the BE and BC are both forward bias. So we still have the emitter, we still have the base, we still have the collector, and then we have the similar, the same, we have the PE0 here, we have the NB0 here, we have the PC0 here. So this is a PE0, NB0, PC0, and in between we have the space charged with the depletion region. So to be more easily to plot, so I have to move this one and put this as a little bit lower. So again, the BE is a forward bias, so we have the same distribution here, where the PX prime should follow the exponential decay here. And also, but now because of the BC is always also forward bias, so since this is forward bias, so that means this point is not starting from 0. The reason starting from 0 here is reverse bias, but now this is forward bias, so therefore this will be somewhere here, and then start to exponential decay. And then in the between the base region, which will be, let me try to, so in the base region will be this one, and because of the junction of the base in the left and right are forward bias, so then the minority K distribution cannot be 0, so we will have here, and this will become here, so then we will have this one, so that's a BX here. By the way, just one small reminder that some of you actually will try to check. I would say very appreciate that everyone is read the slide and then try to check my plotting in the very accurate way. Say sometimes it's a little bit higher, a little bit larger, a little bit lower. But I would say because I'm drawing here by using my hand, so they might be having some mistake here, especially the position. So anyhow, the accurate position, you still need to check the textbook because it's very difficult to draw everything in the very precise way. But my point is that this is more like the schematically to let you understand how this graph is being generated here. Of course, if you have a little bit concern about how the real plot is, you should check the textbook to check the beautiful picture in the textbook. But the concept definitely will be the same, but it just might be the position is not that precise. So this is a case under the saturation, and similarly we can quickly draw again under the cutoff. So the cutoff is this is not correct, so the cutoff is the everything is under the reverse bias. So if we consider everything under reverse bias, that would be, this is a E, B, C, N++, P+, N, and then the P E0, N B0, PC0, PE0, NB0, and then the PC0 here, and then the depletion region here. This is a depletion region. And then when we consider the reverse bias, the things we need to remember is that in the edge of the depletion region is always 0. So that means this always be 0. So therefore, the distribution here is the equilibrium and back to the 0, because this is a reverse bias. And also this is 0, this is 0. So then it should be in this way. And also in the collector the same. This must be 0. So this will be here. So this is a PCXS prime and NBX and PEX prime. So that's the case for the cutoff. And also regarding for the inverse active, this is for the inverse active. So now we still have the E, B, C, and then we have the PE0, NB0. Oh, sorry, it should be a little bit lower, and this one here. And then because of still the same, we are considering N++, P+, and N here. So then in this case we have the PE0, NB0, and PC0 here. And then this is a space charge region. Space charge region here. Space charge region here. So therefore, because right now the inverse active is a B reverse BC forward. By the way, this is another B reverse and then BC forward. So the BC forward, so following the same one we plot for the forward bias. So we were starting from here and have the decrease from this one. So that's a to have a better visualize. I think it's better I put this as a little bit lower. So we have the PC here. X prime prime, and also the same. We're starting from here. This is a NBX, but now because EB junction is a reverse bias, so it must be 0 at the EB junction. And also we have this one, and then the same for this is a reverse bias, so it must be starting from the 0, and then in the end go back to the P0. So that's a PX prime here. So this is in the case of the inverse active. So in anyhow, if you're under the forward bias, under forward active, and that's enough because the sand is the others are very similar, but the most important is the forward active, which will be this one. Forward active part here. So when we consider the forward active operation mode, is a BE junction is under the forward bias. And then the BC junction is under the reverse bias. So that means that in this case, the forward and reverse bias will cause a band diagram like in this way. So this is a BJT from the NPN. This is a N. This is a NPN. And because of forward bias here, so the barrier here is reduced. And because of the reverse bias here, actually the barrier here is increased. And then from this band diagram, you can start have a little bit sense that how the carrier electron can be flowed from left to right because of this barrier reduced, so the electron can start to overcome barrier and reach to the base side. And once to reach the base side, because of this, there's a high slope. There's a very large slope, very steep barrier here. So the electrons here can be accelerated and reach to the collector side. And that's, in the end, cause the current that can be sensed in the collector here. So that's one of the reason that how this can, the device can be have the current in the BJT. So I will probably stop here because of the next one is very important. It start to getting very detailed to explain how the current being transposed in the BJT, that where the idea is still very similar to the MOSFET. First, we have a diffusion, and then in the end will be swept by the electric field. So we will side by side to compare the MOSFET and also the BJT in the next time. So we will stop here. And by the way, just a reminder that so the next Monday we will use last 1 hour, probably last half hour, depends on the progress, to announce the result and talk about a little bit for the midterm exam. I'm sorry that it takes a little bit longer time because of we have more than 70 students here. It takes a quite long time for the grading, and also due to the semester now is getting shorter, so everything is squeezed. The schedule are very tight, so then in the end that we have to. Also today, the reason that I don't announce, actually it's already finished grading, but today I don't announce because I can expect the people come in the Wednesday evening is getting, it must be not enough student. If I announce, I dispute the result to you. I have to do it again on Monday because it's only like the partial student will be present here. So that's one thing. And another thing that some of you actually write email to ask me about the final exam. So we will have a final exam just next Thursday, and then everything you can bring. So it doesn't matter for the notebook, iPad, calculator, slide, whatever textbook you can bring. But I would say that the more things you bring, usually the lower score probably you will get, because of the more things you bring, that means that you are not familiar with everything. You will spend too much time in finding the right answer, because if you are not familiar with, you pretty rely on the resource you will have. Actually in the end you will lose a lot of time to search to the right equation. And also another thing I want to remind that actually I upload, because due to the time schedule, we won't have the time to have another homework, but it's fine. That's just as a homework that everyone can self-practice. So I already uploaded the homework for the 8 and 9 yesterday, so you can check it out, and the solution is already there, but you have to study because that's also related to the final exam. So that's all. So we will see each other on next Monday.